Hi everybody, I wanted to put a little video together for sections 3.4 and 3.5, some of the things that we haven't gotten to discuss in class yet. So in 3.4 we were talking about factors for different numbers, and just to backtrack a tiny bit, when we take a look at what we know to be the factors of 10 as an example, we ask ourselves what divides into 10 evenly. So we know that the factors of 10 are 1 and 10, 2 and 5. So if we list them in increasing order, we have 1, 2, 5, and 10. What I was showing you at the tail end of our lecture, our last day together, was how we can use prime factorization in order to do this using a different method. So with prime factorization, we first have to get 10 in its prime factored form, and we know that 10 can be broken down as 2 times 5. So each one of those happens to be prime. And if we write this in its factored form, 10 is really 2 to the power of 1 multiplied by 5 to the power of 1. And it's kind of nice to put that 1 there as a bit of a placeholder to remind yourself that really we have one of each of those primes. The method we were exploring further then said, let's make a list, and that list can include all of the possible options for base 2 and base 5 when we look at the factors of 10 in general. So if we think about options for, first of all, base 2, we can really think about that as 2 to some power a. If we list those options, I know at most I have 2 to the power of 1, but we could have 2 to the power of 0 as well. So we have 2 to the power of 0 and 2 to the power of 1. If we do the same thing for options and say, what are our options for, let's say, the base 5 this time, we can call that 5 to the power of b, some different power. Those options would be 5 to the power of 0, or at most 5 to the power of 1, because we can see in prime factored form, we have at most 2 to the power of 1 and 5 to the power of 1. From there, what we were doing is saying, how can we combine all of these options for prime bases? So if we multiply 2 to the power of 0 with 5 to the power of 0, that's going to give us one of the factors of 10. So 2 to the power of 0 multiplied by 5 to the power of 0 is equal to 1 times 1, or really 1. Well, we already know 1 is a factor, so it's checking out so far. Another option, though, is if we start with 2 to the power of 0 and multiply it by the other alternative for base 5, and that would be 5 to the power of 1. So 2 to the power of 0, rather, multiplied by 5 to the power of 1 instead is going to be 1 times 5, or 5. So there's another factor from our list for factors of 10. Now, we might not be starting with 2 to the power of 0, but instead starting with 2 to the power of 1. So if we multiply our other options, 2 to the power of 1 could be multiplied by 5 to the power of 0, resulting in 2 times 1, or 2. There's our third factor of 10. Or we could have 2 to the power of 1 times 5 to the power of 1. And if we multiply those results together, we get 2 times 5, or 10, which is really that fourth factor. Now, what we want to explore a little bit further is how we can actually predict or know how many factors we have for any given whole number. What we ended up with when we explored the factors of 10 were really 4 total factors, or the number of factors was 4 in total. Now that's closely linked to, or it is linked to, the number of options we have for each base. And here's how we can explore that a little bit further. If I look at my options for base 2, I have 2 options for base 2. It could be 2 to the power of 0 or 2 to the power of 1. If I look at base 5, I actually have 2 options here as well. You might want to think about this like the fundamental counting principle, or combinations. Of each of those 2 options for base 2, I could choose one of those options. Out of those 2 options for base 5, I could choose one of those options. So 2 choose 1 in both cases, when we multiply them together, give us 2 times 2, or 4 total combinations. So the number of factors, again, is linked to the power for every prime base. At the end of our last lesson, when we were in person, we really said the number of factors that you have for any given whole number n can be derived by the following formula. So we say if we know that we are in prime factored form, or we have the prime factorization of n, we take each of those powers for those prime bases and we add 1 to it before we multiply. So we say, for example, we have 2 to the power of 1, but we actually have 1 plus 1 options because we have 2 to the power of 0 or 2 to the power of 1. So again, you take that single highest power for your prime base and add 1 to it. If I take those two options for base 2 and I multiply that by the two options we have for base 5, again, that's your highest power for base 5 plus 1, multiplying those together would give us the total number of factors. So in this case, again, 2 times 2 would give us a total of 4. To recap the last example we had on this slide, example number 2, where it says how many factors are there in 2 to the power of 2 times 3 to the power of 2? We don't have to multiply that all together and realize that's 4 times 9 or 36. Really, I just want to know how many factors there are if that's the prime factorization for the whole number we're looking a little bit closer at. So in this case, again, our whole task is to take the very highest power you have for any prime. So in this case, we have 2 to the power of 2. And we know that if using our formula, we take that power and we add 1 to it. So k1 plus 1 in this situation is going to be 2 plus 1. And then we do the same for every prime base that we see throughout. So for base 3 as our prime base again, we have 2 in our power position. So we're really going to multiply by another 2 plus 1. So that's your k2 plus 1. That exhausts all of our options for primes. So here if I have 2 plus 1 multiplied by another 2 plus 1, that really is 3 times 3. Or in this case, 9 factors for 2 squared times 3 squared, or 36. So if I wanted to find or list all of the factors, I would know that there should be 9 when we're all done. When we take a look at the examples on the next slide, we're really just going to practice determining the number of factors we would have for each of these values. So in example number 3, we're asking you to determine how many factors there are in 2 to the power of 3 multiplied by 3 to the power of 2 multiplied by 5 to the power of 4. What I want you to recognize is that all 3 of these are prime number bases. I can't combine any of those bases because they are distinct prime numbers, so they're different from one another. So if we want to know the number of factors we would have, essentially, we're going to be highlighting or looking at those high powers, or those powers rather, attached to each prime. So the number of factors in this case, we're going to start with 3, because that was your power for base 2. So we would say you've got 3 plus 1 options for base 2. If we look at our next prime base, we have a base of 3, but it's a power of 2. So multiply that by 2 options, plus 1 more. And again, we're adding 1 more just as a quick reminder, because if I think about 3 squared as my highest option for base 3, it could be 3 squared or 3 to the power of 1 or 3 to the power of 0. So really that 2 plus 1 is giving me all 3 options. Same thing for 5 to the power of 4. We know that we're going to take that power for the prime base, so that power is 4. If we add 1 more to it, it's going to give us our total number of options for base 5 in that situation. So the number of factors for this is going to be 3 plus 1, which is really 4. Multiply that by 3 and multiply that by 5. So once again, you're multiplying these options together to get a total number of combinations in this case. So 12 times 5 gives us a total of 60 factors if we were to find all of the factors for 2 cubed times 3 squared times 5 to the 4. With example number 4, we're asking you really to do the same thing, but you need to be careful about how your numbers have been presented. In this particular case, we have 4 to the power of 3 multiplied by 25 to the power of 3. Now, what we need to make sure of is that our bases are prime numbers. In this situation, we recognize, or we can see very quickly, that these bases, in fact, are not prime, they're composite. So really, it's our job first to make these prime bases instead. So 4 is a composite number, but I know it can be made up as 2 to the power of 2, or 2 squared. Now, if I have 4 rewritten as 2 to the power of 2, or 2 squared, we still have that external power of 3 applied to that base. So we'll take care of that in just a moment. But same thing needs to happen with 25 to the power of 3. 25 is not a prime number, so I have to basically rewrite this as 5 to the power of 2. We know that 5 squared is the same as 25, but it's still raised to that external power of 3. So if I combine the two powers, I know that 2 raised to the power of 2, or 2 squared raised to the power of 3, means I need to multiply power of a power in this situation. So what we end up with using our exponent rules is 2 to the power of 6 multiplied by 5 to the power of 2 times 3, or 5 to the power of 6. Now that we can recognize or see that these are both prime bases, what we need to do is decide how many options we have for each of those prime bases and multiply all of our options together once again. So if we want to take this and determine the number of factors that we have, now that everything's written nicely in its prime factored form, or prime factorization, the number of factors is going to be, in this case, power of 6 plus 1 for your base 2 options. And we're going to multiply that by another power of 6 plus 1 for your base 5 options. So 6 plus 1 is 7. 7 times 7 gives us a total of 49 factors if we were to determine what all of the factors are for that large number. Notice I'm not even calculating what that large number is, because all we're after here are really the determinations of how many factors you would have if we asked you to list them. For our last example here, we want to take a look and figure out how many factors there are if we're given 14 to the power of 3 multiplied by 36 to the power of 2. Now, before we can just take those powers and add 1 to each of those individual powers and multiply all those options together, we really need to make sure that we've got prime number bases before we get any further. So 14 is definitely not prime. We know that 14 written in its prime factorization, or prime factored form, would be 2 times 7. Now that's still raised to the external power of 3. If we do the same thing for 36, and we can pause here if you like, but if you want to break down 36 and do a little bit of mental math here, 36 is really 9 times 4. Both of those are composite numbers, but 4 is really 2 squared, and 9 is really 3 squared. So if that kind of work you want to do on scrap paper or over in the margin, please do so, but confirm that really 36 can be written as 2 squared times 3 squared. Again, this is 36 raised to an additional power of 2, so you want to make sure that you've got that external power of 2 as well. Now, what's happening here is in some situations we're having multiple powers attached to the same base, so we have to go back and use our exponent rules in order to get rid of these brackets and be able to put some of these bases together in a more simplified form. So if I take a look at our first set of brackets where we have 2 times 7 to the power of 3, I know that that power of 3 really distributes. We know exponentiation distributes over multiplication. So we have essentially, if we carry out that multiplication, we've got 2 to the power of 3. There's an imaginary power of 1 sitting with that base of 2 as it is right now. So that imaginary 1 times 3 would be 3. Same thing for power of 1 where we have 7 as our base. So you get 2 to the power of 3 times 7 to the power of 3 in that first set of brackets. When we open up that second set of brackets, again, that external power of 2 exponentiation will distribute through multiplication as well. So we bring that power and apply it to both of those bases inside those brackets. So you'd have 2 to the power of 2 times 2, which is 4, multiplied by 3 to the power of 2 times 2, which is 4 as well. So at this stage, we can recognize that yes, all of these bases are prime, but one other little thing seems to be nagging for us right now. We have bases of 2 in 2 different places, and we know that multiplication is commutative. So if we wanted to put those 2 side by side, or at least group them together, we could write the total number of base 2 or 2's rather that we have. So this becomes 2 to the power of 3 plus 4. Remember, you add your powers when you multiply bases that match. So 2 to the power of 3 plus 4 is really 2 to the power of 7. We can multiply that by 3 to the power of 4 if you want to go in increasing order of bases. And we're multiplying that by 7 to the power of 3. At this stage, because we have all of our primes combined and we know exactly how many options we have for each prime base, we can go ahead and say that the number of factors we would have in this situation is going to be the power of 7 plus 1. Again, you're adding one more option because you have, let's say, 2 to the power of 0 if you want to think about it that way. We also have 4 plus 1 options for your base 3, and we have 3 plus 1 options for your base 7. So this total becomes 8 multiplied by 5 multiplied by 4. So you should get a total of 160 options, or in terms of the number of factors you would have for that particular value. So if we take 14 to the power of 3 and multiply it by 36 to the power of 2, we would end up with 160 total factors. Now that would take us all day. So all we're asking you to do in this scenario is determine how many factors you would have, not actually what those factors are. So in summary, in section 3.4, what we were doing, we're taking a look initially at how to find factors for any given whole number. And what we want to do is give you some of these other methods for finding factors, aside from tried and true, see if something is divisible by. So when you want to start using these processes for determining not only factors, but the number of factors, we need to make sure that you're always writing your whole number in its prime factorization form, or in its prime factored form. Aside from that, the numbers of choices that you would have for every base is always going to be one greater than the power that you begin with. And again, we want to remind you that that's so that we can include, for example, power of 0 for any given base. So if we have the prime factored form for a given whole number, and we're writing that prime factored form in a way that's familiar. We've seen this multiple times now already, where you have every prime base raised to the factor that it corresponds to. So if P1 is your first prime base, K1 is the power that it is applied to, or that applies to it. So what we say, or what we can determine from here, is that the total number of factors that you would have for n always asks you to find k plus 1, so that initial prime base power plus 1, and you continue to multiply those powers plus 1 together until you exhaust all of your prime base options. So once again, prime factorization is critical in this type of question, or in these types of skills. And you want to always remember that you're taking those powers and you're adding 1 to each of those powers before you multiply to find all of the options, or all of the possible factors for any whole number n. We're going to continue our discussion with factors in general, but we're going to focus in 3.5 on what we call the greatest common divisor, or the lowest common multiple. We're going to start with the greatest common divisor and talk a little bit about what that means. So the greatest common divisor between any 2 given values, or 2 given numbers, and we're going to call those numbers A and B, is essentially asking us what the greatest possible divisor is for both of those. So sometimes you may in previous experiences hear this as something we call the greatest common factor. So we're saying if you can imagine the factors for two given numbers, what would be the greatest factor that happens to be common to both lists? So GCD and GCF are talking about the same thing. So in some places or in some resources, you'll hear it being called the greatest common factor. We're going to tend to use greatest common divisor for this module. So if you're going to find the greatest common divisor between two given numbers, you can basically list all of the factors of A or all of the factors of B, and then you can identify the largest or the greatest factor that happens to be common to both. Now there's another strategy I'm going to show you initially here, and that's by using Venn diagrams to identify those common factors, and then we can pick the greatest from that list. So to explore this a little bit further, let's take a look at finding the greatest common divisor, or the GCD, for the two values we're given, 12 and 42. So first, what we'd like to do is list the factors of 42. So we know what factors or what's evenly divisible. So if I want to list factors, again, of 12, we're going to start there. And the factors of 12 are 1 times 12. And sometimes this is sort of an old school way of doing this. I know that 1 times 12 gives me 12. 2 and 6 are factors of 12, so I list 2 and 6. And then I know 3 times 4 gives me 12 as well. And that exhausts my list of factors for the number 12. We want to do the same thing for all factors for 42 as well. And this gets to be a little bit more difficult because 42 is a slightly larger number. But if you need to take a moment to sort of think about what the factors of 42 are, please pause now. You're welcome to do that. But I know that 1 times 42 is how we can get 42. I know that 42 is an even number, so it divides by 2. 2 times 21 gives me 42 as well. We're going to talk about divisibility rules eventually. I know 3 divides 42, so 42 divided by 3 would be 14, so 3 and 14 would be factors. Aside from that, 6 times 7 is 42 as well. So what we've got is our list of factors for 42, and what we need to identify are common factors between those lists. So if I circle anything that's common between these two, I see 1 is common, I see 2 is common to both lists, I see 3 is common to both lists, and I see 6 is common to both lists, and really 6 is the highest or the greatest. So in this particular situation, we would say that the GCF turns out to be 6. Again, GCF, or we can say GCD, greatest common divisor, is really the same thing. Another method for finding a greatest common divisor, or the greatest common divisor between two values, is also by using a Venn diagram. A Venn diagram can help us organize the factors in such a way that we can see what is common to both of those lists, because we'll be looking for the intersection of two spaces in that Venn diagram, or of two sets. So create a Venn diagram where one of those sets represents all factors of 12. Your second set will be introducing all factors of 42, and just be mindful that there's an intersection that happens here. There is overlapping information where factors are common to both lists. So take a moment and create that Venn diagram. If we show factors of, let's say, 12 on the left-hand side, 1, 2, 3, 4, and 6 are all common. So we want to make sure that that is in the intersection space between these two. So we've got 1, 2, 3, and 6 in the intersection between factors of 12 and factors of 42. Aside from that, the factors that I don't have represented in our Venn diagram so far are the factors 4 and 12. So I'm going to include those as factors of 12. Now, what we haven't accounted for factors of 42 are the values 7, 14, 21, and 42. So if we think about these sets, we can see that the intersection's happening for 1, 2, 3, and 6. And because we're asked to determine what the greatest common divisor is, or what the greatest common factor is between these two lists, we can identify that very quickly and say it must be 6, because that's the highest value in the intersection between those two. So once again, we're exploring a couple of different methods to find the greatest common divisor or the greatest common factor. So what we'd like to talk about next is something called the lowest common multiple, or the LCM. Again, this should be a fairly familiar term for you. So when we talk about the least common multiple or lowest common multiple between two values A and B, really we're looking for the lowest number that is a multiple of both A and B. Now, just a quick reminder, there's no such thing as the greatest common multiple, because if we think about multiples and we don't put an upper limit on it, you could list multiples forever and ever. So there has to be a lowest common multiple that we find, because we don't want to keep finding multiples or using larger and larger values indefinitely. So to find the LCM between two values A and B, we can list all multiples and then decide or identify which multiple happens to be common to both lists and which of those options is the lowest. So let's take a look at how to do that and how to create a Venn diagram to show the same thing for LCMs. So the second example that you see here, example number 2 on your screen, says find the LCM, or least common multiple, between 4 and 6. So if I wanted to just list things, I could say the multiples of 6, or the multiples of 4, let's start there rather. You would start with 4, and basically you're counting by 4s from here. So 4 would be a multiple of 4, then 4 plus 4 would be 8, 8 plus 4 would be 12, 12 plus 4 would be 16, 16 plus 4 would be 20, 20 plus 4 would be 24, and so on. And I'm going to put 3 dots here to signify that that pattern continues indefinitely. So if we do the same thing and want to list the multiples this time of 6, we start at 6 and then we add 6. So 6 is a multiple of 6. 6 and 6 would be 12. We know adding 6 would give us 18, and then we would have 24. We add 6 more and we'd get 30. So we're really just counting by sixes. And I want to sort of stop because I think we've exhausted enough options at this stage. So if I take a look at what's common between those lists for just the values that I've included, we can see that 24 is common to both lists, but there's actually a smaller value or a lower value here. So we can see or identify that 12 happens to be the very least common multiple for those two lists. So given LCM values, or we're being asked to find the LCM for both 4 and 6, we would say that our answer in this situation is 12. 12 is the lowest common multiple that we can identify for both of those lists. Once again, you could use Venn diagrams to show the same information or to find the lowest common multiple between 4 and 6 as well. So we're going to do that. We're going to create a Venn diagram with a point of intersection between them. So there will be some overlapping values in that intersection between the two sets. So create your Venn diagram and see if you can imagine where to put these numbers, or at least some of the multiples that we've been exploring so far with the LCM for 4 and 6. So you can see I've created a Venn diagram here where I've got a set representing multiples of 4, a set representing multiples of 6, and what we want to do is start filling in where those numbers belong. So if we have a multiple of 4, the first multiple of 4 we can think of is actually 4. That's not common for multiples of 6 as well. It's not overlapping, so we don't put it in that point of intersection. The next multiple of 4 is 8. Again, that's not common as a multiple of 6 as well, so we leave it outside that intersection area. We've got 4, 8, and then we would have 12. Now we know that 12 is also a multiple of 6, so we can fill it in the center where the intersection of those two sets is occurring. So we've got 4, 8, 12. We've got 16 as a multiple of 4. Again, that's not common to both lists. We've got 20 that is a multiple of 4. And we've also got 24, which is a multiple of 4, but that's also a multiple of 6. So we put that in the middle. Now, aside from that, if we want to fill in a few multiples of 6, you're welcome to do that. Multiples of 6 are 6, and then 12, again, is in that intersection. The next multiple would be 18, which is not common to both. We would have 24, and then we would have 30, which is not common to both. And we can continue indefinitely. So if you want to put 3 dots here to recognize that there will be more multiples of 6 if we decided to continue, there would be more common multiples between 4 and 6, and there would be more multiples of 4, again, if we wanted to continue. So what we're looking for an LCM, just as a reminder, is the lowest common multiple. Again, we would never ask you for a highest common multiple because we would never get a highest common multiple. We would just keep adding more multiples as we go higher and higher. So the LCM in this case, again, we can identify as 12 by using a Venn diagram. As we found for finding factors of really large numbers or continuing to find multiples, sometimes that work can be quite tedious, and we can actually give you an alternative method for finding both greatest common divisors or greatest common factors and least common multiples. So we're going to start with an alternative method for finding a GCD or greatest common divisor. Now what this is going to require first of all is prime factorization. So that takes us back to making sure that we're breaking down numbers, or whole numbers rather, into the product of their prime numbers. So when we are asking you to find the greatest common divisor for 2 specific values, we'll call those A and B, the first thing you want to do is really just do the prime factorization. So what is the prime factorization for A, and what is the prime factorization for B? Once you have the prime factorizations for A and B set, for each prime, what you're going to do is actually select the smallest power for each prime number and include that factor in your answer. What I want you to note here is it's almost counterintuitive at first glance because we're looking for the greatest common divisor, but we actually have to pick the smallest or tiniest power for each prime. By choosing that smallest power, though, we're actually finding the largest collection of primes that can be contained by both values that were given, so by both A and B. Hopefully this will make better sense once we get into some examples where we're using this method to find the greatest common divisor. So let's do that now with example number 3 that you see on your slide. If we ask you to find the greatest common divisor between 12 and 42, we've already found that. We did that a few moments ago and we said the GCD was actually 6, but we're going to use this method of prime factorization in order to verify that. So the first step says find prime factorizations for both A and B. So we'll do that for 12 first. We know the prime factorization for 12, if we have to go back to our factor tree, would be 4 times 3. And again, 4 is not prime, so we continue and say that that's 2 times 2 multiplied by 3 as well. So the prime factorization for 12 is 2 squared times 3. So we're combining those base 2's. If we do the same thing for 42, we can see that 42 can be broken down as 2 times 21. And again, 2 is prime, but 21 must be factored further as 3 times 7. So the prime factorization for 42 would be 2 times 3 times 7. Now from here, what we want to make sure of is that when we find your LCD, so I'm going to start marking my work here. If I want to find my LCD, I have to take every prime base that I see, and I'm going to choose its very smallest power in either one of those lists. So let's compare bases of 2. I have 2 to the power of 2, and I have 2 to kind of a sneaky little power of 1 when I compare 12 with 42. So if I compare 12 with 42 and we're asked to find the smallest power possible, we know that 2 to the power of 1 is going to be the very smallest power that I can use. So my LCD is going to include 2 to the power of 1. If we now move on to 3, I've got 3 to the power of 1 in both places. So it doesn't matter, of course, which base and power I choose because they're the same. 3 to the power of 1 would be the lowest possible power, or smallest power, for that prime. Now be a little bit careful with 7. What I want you to recognize is that 7 is a prime number that we have when we factor 42, but I don't see a 7 when I look at the prime factors for 12. This is where you need to imagine that 7 is actually one of those prime factors for 12, but we have to be careful because if I say, yes, multiply that by 7, I'm changing my result. It's no longer going to be a 12. But if I say this is 7 to the power of 0, we know that 7 to the power of 0 is just 1. So now we can compare bases of 7 and say 12 has 7 as its base to the power of 0, and we know that 42 has 7 as its base with the power of 1. So again, if we were going to pick the very lowest power between those two, we compare power of 0 to power of 1, we would have to include 7 to the power of 0 because power of 0 is lower than power of 1. So from here, we just find the product of these. We multiply them out. 2 times 3 times 1 gives us 6. And once again, we know that the LCD for both 12 and 42, so the lowest common or least common divisor for 12 and 42 is 6, but we used a slightly different method this time in order to find it. We will come back and practice that method for finding greatest common divisors, but we're going to pivot a little bit and talk about how that method can be used in a very similar fashion to find least common multiples or lowest common multiples as well. So you're going to find that the steps for finding an LCM or a GCD start with the same process. We need to find the prime factorizations for any two numbers that we want to find a lowest common multiple for. So if we're trying to find the LCM for A and B, we need to find the prime factorizations first for A and B. From there, again, initially it might seem counterintuitive until you see some examples at work, but the lowest common multiple actually requires you to find or include the largest power for any prime base. We have to include those largest powers as factors in our final answer when we're looking for the LCM for A and B. And again, by choosing the very largest power, you're actually finding the smallest number that can contain all of the primes from both A and B. Again, until you get your hands on some examples, this might be a little bit difficult to wrap your head around. So let's just jump in and see if we can find, for example, number 4 here, the LCM for both 4 and 6. We've already done the work for this, right? We know that the answer is going to be 12, but we're going to confirm that with this brand new method where we start initially with prime factorization for both 4 and 6. Now, I don't think we have to do a factor tree for 4 and 6. We know that the factors of 4 are really 2 times 2. So if we want to write 4 in prime factored form, we would say that that's 2 to the power of 2. If we do the same thing for 6, our factor tree again would be pretty teeny tiny. We'd have 2 times 3 to give us 6, and those are both primes. So you have 2 to the power of 1 if you want to use a little placeholder there, and you have 3 to the power of 1 as well. So this method requires that if we're finding the lowest common multiple for 4 and 6, we're going to pick every prime that we see in terms of our bases. But instead of picking the smallest power of those primes, we actually pick the largest power of those primes. So let's compare our bases of 2. We have 2 to the power of 2 and we have 2 to the power of 1. So when we look at 2 to the power of 2 versus 2 to the power of 1, again, we recognize very quickly that 2 is the largest power, so that's the one we need to include. So we've got 2 to the power of 2 as part of our lowest common multiple so far. Aside from that, I have a prime base of 3, and that's 3 to the power of 1. Just like we did in the previous example where we had no base of 7 in both lists, we wanted to make sure that we account for a base 3, but we don't want to mess around with the value of 4. So what we can do is say, imagine we take 4, break it down as 2 squared, but if you'd like, you can also say that's multiplied by 3 to the power of 0. We know that there are no 3's essentially as part of that prime factorization. So once again, when we compare those powers, power of 0 and power of 1, for the LCM, we want to pick the very highest of those powers. So in this situation, we would say let's multiply 2 to the power of 2 by 3 to the highest power we can identify, which is 3 to the power of 1. So carrying out the multiplication, 2 squared is 4. 4 times 3 gives us 12. And I know that using Venn diagrams or by listing common multiples for 4 and 6, we were able to see that the LCM, the lowest common multiple between 4 and 6, was in fact 12. Let's try the last example that we see here on the slide, example number 5, where we're asking to find the LCM for 12 and 42. Once again, our first task is to write both 12 and 42 in prime factored form or in their prime factorizations. So 12 we know is going to be 2 squared times 3. So again, if you want to pause here and just verify that we've got the prime factorization for these values, please go ahead. But we're going to do the same thing for 42. So again, the prime factorization for 42, if you'd like to look back at your previous work, is going to be 2 times 3 times 7. So if we think about 2 times 3 is 6, 6 times 7 is 42, that's a quick way to verify that we've got our prime factorization done correctly. Aside from that, please remember that you're always trying to make sure that each of those bases is in fact a prime number. So we're kind of getting the work out of the way for example number 5, and now we can just pull some of those bases together to make sure that we've got all of the factors that we need for the true LCM between 12 and 42. So if we want the lowest common multiple of 12 and 42, we can start by examining the 2's. If I examine the powers that are attached to base 2, we have 2 squared or 2 to a sneaky little power 1. So again, for an LCM, we pick the highest or the largest power. So we have to have 2 to the power of 2 as one of our factors. Now, if we want to compare the bases of 3, we've got 3 to the power of 1 in both places. So if we want to pick the highest power, they're both the same. So we would say let's multiply that rather by 3 to the power of 1. And now we have a base 7, but we don't have another 7 when we look at factors of 12. So once again, if you'd like to imagine that this is 7 to the power of 0, if we compare 7 to the power of 0 with 7 to the power of 1, I can connect those two if you like. 7 to the power of 0 and 7 to the power of 1, if we identify the very highest power, we know that the highest power here is 7 to the power of 1, so that needs to be included as part of our LCM factors, or the factors that make up our LCM. So to work this out, we've got 4 essentially times 3, which is 12. 12 times 7 would give us 84. So if we listed multiples of 12 and multiples of 42, eventually both of those lists would contain 84, and 84 would be the very smallest value contained in those lists of common multiples. Now, there's an interesting relationship between lowest common multiples and greatest common divisors. And we're going to explore what that looks like by giving you an example that we really just tackled. So if I asked you to find the greatest common divisor between 12 and 42, we know that the answer turns out to be 6. We don't have to redo that problem. We know that the GCD for 12 and 42 turns out to be 6 as a value. The lowest common multiple between those same two values, 12 and 42, the LCM, turns out to be 84. So if we wanted to play around with these numbers just a little bit and multiply those two together, so in this next step, we're asking you to explore that multiplication and say if you took the GCD of 12 and 42 and multiplied it by the lowest common multiple of 12 and 42, you would get 6 times 84, or in fact 504. Now you might not think much of that number, but it's very interesting if you're also going to check what happens when you multiply A and B together. So if I want the GCD of 12 and 42 or the LCM of 12 and 42, what happens when we multiply 12 by 42 itself? Well, lo and behold, we get the same number. It's 504. So it actually gives us a formula that we can use as long as we know A and B, and we're being asked to find either the greatest common divisor or the lowest common multiple. So what we're saying here is that if we were to rewrite the formula and make the substitutions, so if we know that we're looking for the GCD of 12 and 42, the formula says take the GCD of 12 and 42, multiply that by the LCM of 12 and 42, so your same A's and B's, and what you'll end up with is the same value as 12 times 42, or A times B on its own. So the GCD of 12 and 42 was 6, the LCM of 12 and 42 was 84. If we did that math, we would get a result of 504. But if we also multiplied 12 by 42, we would get the same value of 504. So this is really just verification or proof of the formula that we're highlighting at the bottom of your screen. So it's basically true, and here's sort of why. This is true because if you take the GCD of A and B and we list those as factors, and we multiply that by the lowest common multiple for A and B, again, list all of those factors, you're going to recognize that it contains all of the same primes as A times B, but they're just in a different order. So if you want to sort of pause here and go back and do that verification or proof, you're more than welcome to. But essentially what we're trying to get at is if you know either the GCD for two given values or you know the lowest common multiple for those same two values, you can actually use this formula as a bit of a shortcut to find the other missing information pieces. So let's put this little relationship or this equation to the test. So basically, again, using this equation tells us that we can use the GCD to find the LCM, or vice versa. We can use the LCM to find the GCD for the same two given values, A and B. So let's see what this looks like in practice. So with example number 6, we see that we're looking for the GCD of 4 and 30. And we're looking for the LCM for the same combination, 4 and 30. So the same two given values, A and B. So it doesn't matter which one you want to find, we can use prime factorization to get us started to find, let's say, the GCD, just because that's appearing here first. So when we use prime factorization, again, we have to think about the prime factorization for 4, which is pretty straightforward. This is just 2 squared. If we do the same thing for, let's say, 30, and write it in its prime factored form, or with prime factorization, in my mind, I break down 30 by dividing by 2 first, so I think about 2 times 15, but again, 15 is prime, so we've got a little more breakdown to do to get prime factorization. What we end up with here is 2 times 3 times 5. And if you'd like to put little ones there as placeholders, you're welcome to do so. So the GCD the greatest common divisor for both 4 and 30, now that I've got my list of primes, is as easy as selecting your smallest power for any given factor. So just as a quick reminder, the greatest common divisor has to have the teeniest, tiniest powers, so the smallest powers. Again, so if we look at our 2's, we have 2 to the power of 1 versus 2 to the power of 2. We know that 2 to the power of 1 is the smallest. Now, aside from that, we have bases of 3 and bases of 5. I don't have any bases of 3 written when I think about or look at the number 4. So remember, you can say that that's actually multiplied by 3 to the power of 0 because I have no 3's in that base. Same thing with 5's. We actually have 5 to the power of 0. So keeping that in mind, the greatest common divisor between 4 and 30 would have 2 to the power of 1 because that's the smallest power. We would have 3 to the power of 0 as part of my multiples of bases, rather. And we would have 5 to the power of 0 as well. So now when we work this out, 2 times 1 is really just 2. So the greatest common divisor between 4 and 30 would be 2. Now remember, GCD and GCF are the same thing, the greatest common factor. If I think about factors of 4, as an example, the only factors of 4 are 1 and 4, or 2 times 2, right? 2 is a factor of 4. 4 doesn't divide evenly into 30s, so it makes sense that only 2 is the greatest common denominator. It seems teeny tiny, but again, 4 is a pretty small number to be working with. So the greatest common divisor in this case is 2 when we're looking at 4 and 30. Now looking at the formula that we have, and I'm going to reset my work here by saying, if you take the greatest common divisor between 4 and 30, and you multiply it by the LCM for both 4 and 30, you'll get the same result as multiplying A times B. So in this case, we know A is 4 and B is 30. So now this is just a matter of substitutions. The greatest common divisor for 4 and 30 we already found was 2. If I multiply that by the LCM of both 4 and 30, my final result is going to be 120. So all I need to do at this stage is divide by 2 in order to solve or find the LCM. So if we divide both sides of this equation by 2 to solve, we can see that the LCM result for 4 and 30 is going to be 120 divided by 2, or 60. And we didn't have to do any of the work. Oh, my dog wants to say hi. With the last example on this slide, we're going to find the GCD and the LCM for 3 and 29. And once again, it doesn't matter whether you find the GCD and find the LCM or vice versa. This time, just for changing it up, we'll start with the LCM. So if we want to find the GCD for 3 and 29, and we also want to find the LCM for the same AB values, 3 and 29. This time, like I said, let's find the LCM. So the good news is we've chosen 2 prime numbers, so these are pretty straightforward. If I think about prime factorization for 3, that's 3 to the power of 1, and that's about it. So 29 in its prime factored form is 29 to the power of 1. There's no way for us to break these down because they are already prime. So if we wanted to find the LCM of these two, the LCM, the lowest common multiple for both 3 and 29, would mean that we have to choose the very highest power this time. Well, there isn't a whole lot to choose from. We've got 3 with a base 3 with a power of 1. And again, if we want to imagine a base 3 as well as part of the factorization for 29, we would just have to say that that's 3 to the power of 0. Same thing with 29. We have 29 to the power of 0, so we're just using those to hold place or hold space. because we know for an LCM, we want to pick the single highest power for any given base. So we see that at the most, or at the highest end, 3 to the power of 1 is going to need to be included, rather, and so is 29 to the power of 1. So the LCM for both 3 and 29 really just requires us to multiply 3 by 29. So in this case, what we get is 87 as our total value. So the formula tells us, now that we know the LCM, we can use it to find the greatest common divisor. So once again, now that we know the LCM, we can use the formula to find the GCD. So we're going to say the GCD for 3 and 29 multiplied by the LCM for 3 and 29 is the same as the product of 3 and 29. So 3 times 29 will give us the same value. The GCD is unknown, so I'm going to leave that list here and multiply that by the found information, or the found value. We know that the LCM of 3 and 29 is in fact 87. From here, the right side of the equation can be evaluated, and we know that 3 times 29 is also 87. So in order to find the GCD, we still need to divide, but this time we're dividing both sides of the equation by 87. When you carry out this division, what we recognize is that the GCD, or the greatest common divisor between 3 and 29, turns out to be just 1. 87 divided by 87, anything divided by itself is 1. Now think about factors of 3, factors of 29. Factors of 3 are 1 and 3. Factors of 29 are 1 and 29. So the largest factor common to both lists must be 1. But again, we were able to use the formula in order to figure that out as well. So the purpose of section 3.5 was all about reintroducing you to greatest common divisors, or greatest common factors, and lowest common multiples. So when you're finding either the GCD or the LCM, the first step is to start with prime factorization. So you're going to break things down into their product of prime numbers and make sure that you've got all bases and powers accounted for. Once you have prime factorization completed, the GCD is going to require that you choose the very lowest power for each of those primes. Well, alternatively, the LCM, or lowest common multiple, is going to require that you pick the very highest power for each of those primes. Aside from that, this section also went on to say if you know either the GCD or the LCM, you can use the formula that you see in order to find the other missing pieces of information. So if we're given a common denominator, or the GCD, and we know what values we're dealing with for A and B, this really just becomes a tiny little equation for us to isolate the other variable, or the other missing piece, the other unknown. So from here, folks, please make sure that you're doing some practice problems and finding both the GCD and the LCM on your own. And if there are any questions that you have about this material, I'll be happy to help. Just come see me. Enjoy the rest of your day.